start. Today I'm presenting a detection of objects and trajectories in real time using deep learning by controlled robot. My name is Aygurim Yesenbayeva, and here are my co-authors. We worked at Nazarbayev University in collaboration with robotics and computer science departments. So the next slide, it's all about our motivations and objectives in our research. So we know nowadays that robotics and machine learning is one of the trending areas, and it allows the people to build autonomous vehicles, various robots, to make work autonomously. Most of the robots are now embedded with the sensors, and they allow us to collect many heterogeneous informations. And as well as it allows us to perform any technological operation, especially in extreme environments. So what were our objectives for this research is that we worked on the recognition of object on images, and then we tried to build a trajectory to the objects and then follow these objects. Next, I will talk about what we exactly done in this research. So we're proposing an accurate and robust solutions for detection and localization of objects in real time. And we performed all these tests in our laboratory environment inside of our university. We used the YOLO v3 deep learning algorithm in order to do the training, and we worked on open source images, image data sets. And we also compared with traditional object detection algorithms such as CNN and faster RCNN. So in terms of trajectory detection stuff, we used 2D LiDAR, which does for us very accurate trajectory estimation, and we applied on top of that the polynomial regression to smooth the path to the object. For the comparison of different other cameras which can do the trajectory estimation for us correctly, we compared with the depth camera. We did the necessary work like as an extension for our research to follow the object on using our robot. So the next we will talk object detection and trajectory plot. So that's basically all the steps what we do. We first recognize the object using YOLO v3 algorithm. However, we don't train from scratch in order to make it faster. Using transfer learning, which means that we use pre-trained weights here. So we also, once we determine the object, we start saving all the coordinates in CSV file, and even if the object is moving, we still keep saving all the new coordinates to the CSV file. So as the next step, we plot all this, as a scatter plot, all these coordinates on our path to the object from the robot, and then we apply the polynomial regression in order to smooth this path to the object. So what we've done exactly is, this is how our robots looks. We used a Jaguar 4x4 wheeled mobile robotic platform. So since it does not have embedded LiDAR, we mounted it on the top of our robot. The main disadvantage is that it does not detect any obstacles below this camera. However, it's still accurate for our trajectory estimations. We used also IP camera to get the input from the environment. We used also, as I mentioned earlier, a depth camera for determining the distance to the object. For the client side, we use the Raspberry Pi, which does most of our processing work for us. It basically gets all the input from sensors and sends it to the server, in which case it's our PC, and sends it, of course, by Wi-Fi. So let's get in deeper about how object detection works. So what we've done with object detection, we consider as YOLO v3 as one of the best algorithms for object detection, because it's faster and it can does object detection even using videos. CNN and faster RCNN, we also experimented on them, and since they take fragments of image and then tries to classify it again and again, it's getting a bit slower. We also compared the mean average precisions for these algorithms. In terms of that, faster RCNN may be performing sometimes better than YOLO v3 and takes 5 frames per second, while YOLO v3, if it's done in NVIDIA Titan X graphics processing unit, it can do 30 frames per second, and it's almost like our video stuff. So we're using it for our research mainly. Next, this is about data sets which we used for our research. So we used Google Open Images v4, which is containing 600 classes, 1,743 training images, 41,000 validating, and for testing 126,000 of images. So, however, we used only 4 classes like person, box, chair, mechanical fan, and for Pascal Walk 2007 and Pascal Walk 2012 in total, which has 20 classes, but we extracted only 12, and we used it for our research. We still did training with 2 models. One is on Pascal Walk, which took us 5 days on training with ImageNet backbone, the 4th data set which we have here, that contains additional 53 convolutional layers, and we spent another 2 days on tiny version of that with, again, ImageNet backbone that contains 12 convolutional layers. For real-time test, we chose algorithm with the highest mean average precision. Now let's move about how we do trajectory estimation using cameras like LiDAR, depth camera, and CMOS for our experiment. So it's normally an inexpensive process with radars or lasers. And what it does, it basically locates the object and returns the Cartesian coordinates of that object and plotting a trajectory to it. In our research, we used triangle similarity principle, and for calibrating, for correcting the distortion of photos and videos, we did calibrating of our camera. So here we did the trajectory estimation using depth camera and comparison with RGB camera. So a depth camera itself has an infrared projector, and instead of returning color for each pixel, it returns a depth. So it has it has several resolution modes. However, we use the one which is 848 by 480 because if we take a lower one, the precision gets lower as well. So on the left here, we can see that RGB camera puts a bounding box for our object, and at the class person. It maps basically this bounding box to our depth camera, and then it combines it together in order to determine the trajectory to it. So how we did a localization of it is we used all of v3, which actually returns the coordinates of the center of bounding box. Another way which we used for getting the coordinates is that it might return x, y position, and then height and width of that bounding box. Or the third version is when we just basically gets all the coordinates of the bounding box, and that's the way how we get the position of that object and can get the distance. LiDAR basically converts his polar values to the Cartesian ones, and then returns an array with array of laser scans with 1080 numbers there. So, so as we said earlier, we did a comparison with 3 different cameras. Here we took an experiment with actual distances, 2.75 meters, 5.5 meters, 7.25 meters and 9 meters. That's the location of object from the camera. And we use 3 different cameras here, which are doing their own measurements to the object. And we can see that worse once the object is located far away from the camera, while the CMOS is more or less all the time is even. Actually, 2D LiDAR is pretty accurate with up to 30 meters away from the camera. So that's about our cameras. We also compared with different researchers, which has pretty much similar values. For instance, for CMOS camera here, very similar to our results, and depth camera also does similar range. And for 2D LiDAR, it also has very accurate precision for trajectories. Now, when we applied polynomial regression to smooth our path to the object, we did different experiments here and tried to check how well it fits our path. So we used different scores for root mean square error, squared R, and polynomial degree. So we can see in the first image that it fits pretty well. So of course the results are pretty high. And for the last version, we have some deviations from the past. That's the why the version has a little bit low in terms of error rate. It has a bit poor results. So next one, since 2D LiDAR gives a very accurate results, we use it as a ground truth and trying to compare depth camera and CMOS camera with LiDAR. So in terms of error, depth camera shows the better results, and in terms of Spearman correlation, it also has a very similar results as a LiDAR. So we can see it as depth camera as one which is alternative, could be used for LiDAR rather than CMOS camera. And the final experiment as an extension for our research, we made our robot to follow the object which might be disappearing from the view and then find it again. So initially, if the camera located, let's say here, and then 6.5 meters away, there is an object which gets disappeared from the view of our camera to the right. And that's the way how robot moves to the checkpoint when the object gets disappeared, and then tries to detect the object again. So using the same algorithm. For comparison, we use 3 different cameras and put the results here. So depth cameras, LiDARs, and CMOS cameras, and then we merged all together. Again, we can see that LiDAR and depth camera performs pretty much similar results, while the CMOS one has a bit higher fluctuations, and so we can see some bigger gaps between the coordinates. For conclusion, we used 4 different data sets. We used pre-trained weights for our object detection, which is transfer learning. We used 3 different cameras to detect the trajectories. For the modeling, we used 2 different models, YOLO V3 and YOLO V3 Tiny, as I mentioned earlier. We also applied a polynomial regression to smooth the path, and as an extension, we control our robot, which follows the object. Experiment shows that it's pretty much feasible. As for the future work, we would like to investigate other more efficient algorithms for trajectory prediction and for object tracking on autonomous way rather than controlled way, which we've done. So I guess that's all. Thank you so much for your attention. Any questions, I will be happy to answer.